In this video, what we focus on as we continue our journey through the world of bioanalytical chemistry as applied toward chemical biology, we look here at ultraviolet visible spectroscopy, or UV-VIS for short. When we refer to UV-VIS spectroscopy, what we are looking at is the fact that some compounds absorb light or electromagnetic radiation within the specific region that is encompassed by the UV visible region of the spectrum. So when we talk about UV, we're referring to the region of electromagnetic radiation between 190 and 400 nanometers. The visible region of the spectrum then is between 400 and 800 nanometers. What we will see is that certain functional groups are capable of absorbing radiation in this range. Since the focus of this course, chemical biology, is primarily on biologically relevant molecules, we specifically focus mostly on organic compounds, and so that's why I mentioned here select functional groups absorbing radiation in this range. There are also a variety of inorganic compounds that can absorb radiation in this range as well, but we're going to focus mostly upon the organic side of the spectrum here. So what we're generally looking at here is that select functional groups absorb radiation within this 190 to 800 nanometer UV-VIS range. And those certain functional groups that are capable of absorbing radiation in this range are generally going to fall into a few categories. Specifically, compounds that have pi bonds are very common for absorbing light within this range, or absorbing radiation within this range. Compounds with pi bonds include a huge variety of functional groups like ketones, aldehydes, and esters, amides, and so on, compound functional groups that are very relevant toward chemical biology. Additionally, continuing this theme of pi bonds, conjugation, that pattern of alternating single and double bonds, often causes very strong absorption in the visible region of the spectrum. So when we're talking about conjugation, we're referring to that pattern of double bond, single bond, double bond, single bond, double bond, and then that could continue onward and outward to further conjugate the molecule. And the extent of conjugation would impact the exact wavelength within the spectrum at which the compound absorbed radiation. When we are using UV-VIS, it is generally going to work best for pure compounds. And the reason why it works best for pure compounds is because otherwise the spectrum is very complex and it is difficult or impossible to tell which signal in the spectrum goes with which particular compound. So when we are looking at a UV-VIS spectrum, if we have a spectrum for a relatively pure compound, what we can do is plot, and the spectrometer will read the wavelength in units of nanometers generally. And we can measure this from, say, 190 nanometers all the way up to 800 nanometers if we wanted to measure the full UV-VIS range. And then on the y-axis, we would plot the absorption. And we would see if we were working with a pure compound, there would generally be 2 or 3 distinct absorption maxima within that spectrum. These relative peaks within the spectrum that I just put those blue X's on would be our absorption maxima. And if we're looking at a pure compound and we're comparing that to a standard of that same compound, we would see that the two UV-VIS spectra should match up perfectly, assuming that the compounds are in the same solvent and run at the same pH and the same temperature and things like that. So since we are using this mostly for pure compounds and looking at the specific pattern, we can match the pattern between two compounds to determine whether they are likely the same compound or not. It's one of the tools that will provide evidence for whether two samples contain the same exact compound or not. So we can use it to determine whether two compounds are likely the same. And I say likely the same because it can, in some cases, if you have closely related compounds, they can have very similar or even identical UV spectra. And so we can provide evidence whether two compounds are potentially the same or not. If the two compounds have different UV spectra, then that means they can't be the same. If they have the same UV spectra, then quite possibly they are the same compound. The other primary application of UV-VIS is to quantify pure compounds that absorb light within this range. In order to quantify a pure compound, we can apply the Beer-Lambert law. So the Beer-Lambert law spelled out indicates that A for absorbance is equal to the molar attenuation coefficient or absorptivity of the compound times L, the path length, times C, the concentration of the compound. So I'm going to go ahead and label what each of those letters represent here. So A is the absorptivity. This is what the instrument will measure. E is referred to as the molar attenuation coefficient. And if you're working with a common, well-studied substance such as nucleic acids, this value is well known. For any particular compound, this is going to be a constant. And then L is the optical path length. That's the distance that the light beam or electromagnetic radiation beam is traveling. And so that will be a constant as well when you're using a particular instrument. And then C is the concentration. And so if you have a solution of sample of unknown concentration, you can use this Beer-Lambert law where you are able to determine the absorptivity, because that's what you will measure with the instrument. You can know that the molar attenuation coefficient is constant, the path length is constant within a particular instrument. And so then if these two values are constant and we have measured the absorptivity, the only thing left that we don't know is the concentration. So you can go in and solve for that value. And so very commonly, this is done with samples of, for example, DNA to determine the concentration of DNA, as well as proteins. Commonly, proteins are quantified using UV-VIS absorption as well. So a couple of applications is quantification of proteins and quantification of nucleic acids as well. And both proteins and nucleic acids have generally UV spectra that are very predictable. For nucleic acids, the spectrum is super predictable because when we think about DNA, it's composed, as we learned in the last module, of 4 nucleotides. And so since those 4 nucleotides are repeating, we get a very consistent UV-VIS spectrum that we can measure for DNA. For proteins, there's a bit more variability because the primary amino acids that absorb UV light are things that have conjugation, like our aromatic amino acids, that being tyrosine, phenylalanine, and tryptophan, whereas other amino acids such as alanine and other aliphatic amino acids are not going to have quite the same absorption. But if we assume over the course of an entire protein sequence, that there's going to be an approximate number of aromatic amino acid residues. We can make a good approximation generally about the protein concentration by applying the Beer-Lambert law here and measuring the UV absorption of that particular protein. So hence we can say that UV-VIS is primarily useful for evaluating some structural characteristics of a compound. For example, evaluating whether two compounds are likely the same or have similar functional groups within them, and also applicable for determining the concentration of pure compounds, particularly pure, well-studied compounds such as nucleic acids or proteins, or less well-studied organic molecules such as drug molecules, where we have adequate material to make a standard curve of different concentrations related to the absorption, and then take your unknown and determine its concentration as well, all applying the Beer-Lambert law. So that's our summary of UV-VIS spectroscopy, one of the tools within our arsenal of ways that we can go about determining the structures of organic molecules and evaluating the structures of these organic and biologically relevant compounds.